Team 3.1 presents The Life Star.
The year is 2025. The Earth's average temperature has risen faster than scientists had predicted. It's clear that the goals of the Paris Climate Accord are not going to be met. Extreme weather phenomena such as hurricanes and severe storms are becoming more frequent and causing more damage. A new international initiative is brought forward in search of better data on the atmosphere and pollution. The initiative suggests the creation of a network of data collecting devices that fly around the Earth indefinitely in a way that resembles orbiting satellites. This network will deliver detailed data on air pollution and weather patterns globally, enabling scientists to identify sources of greenhouse gases, make better predictions about climate change, and give more advanced warnings about extreme and ordinary weather. This is a proposal for one such device.
Now, we can start to characterize some objectives we want our project to consist of. Essentially, for our primary objectives, we listed all the necessities of this year's design project: self-propelled and powered on renewable energy while maximizing a useful flight time. Our secondary objectives start to specify goals aimed at the context of our project. Naturally, we want our device to be able to collect appropriate environmental data, hence, we need to make sure our device will be able to carry a suitable load. Finally, to collect a specific set of environmental data, we want to be able to control its elevation with a degree of maneuverability to avoid any potential obstacles in the way. Next, we highlight some of our key requirements with their associated stakeholder source. The environmental agencies, along with meteorologists and scientists, are responsible for most of the need of our project. For successful performance and functionality, we need our design to stay a minimum of 1 meter above the ground for at least 15 minutes while carrying at least half a kilogram. Further, since our design will be outdoors, we needed to operate throughout any weather condition or any time of day and be able to navigate in any direction. The government will need the project to send data spontaneously in order to send alerts of any dangerous weather or environmental condition, while air traffic control would need the device to be compact as possible.
This small chart shows our design requirements and how each design requirement will be achieved, so that when all these factors are put together, the finished product will result in our preliminary design. This is the design that scored the highest based on our decision matrix. The steering or thrust would be produced by one or more propellers. The energy source will come from a solar cell that converts the energy from the sun into an electrical energy, and that electrical energy will be stored in a battery for later use. The lift force is generated through buoyancy by using a gas that is lighter than air, which will keep the vehicle afloat. And finally, the vehicle will be capable of landing in the water because it can float. Here's a rough sketch of our design based on the morphological chart on the previous slide. As you can see, it's a balloon type vehicle that will float, and it can steer with the use of these propellers. It absorbs energy from the solar cell and stores it in a battery and uses sensing equipment and air ballasts to change its altitude and receive and send information.
We have divided our device into three separate systems: energy collection and storage, flight control and sensing, and altitude and flight. The device will receive its energy from the sun. A concentrated photovoltaic will be the most weight-effective way to do this. By concentrating the sun with lightweight and reflected mylar onto a small, efficient solar cell, the same power can be generated from a smaller solar panel as one much larger and heavier. The power generated from the concentrator will need to be converted to a useful voltage before powering onboard systems or being stored in the battery. Calculations involved include solar heating of the system, energy conversion efficiency and maximum energy use, and storage and output. In order to generate power, the device must be pointed at the sun. The direction of the sun will be determined with an array of light sensors. A control system will send instructions to thrusters, which will be used to aim the craft. A variety of sensors will be on board to collect data on desired variables, like atmospheric composition and other physical properties. Some calculations involved for this system include the development and tuning of a control system for aiming the device, efficiency and performance analysis of different orientation methods, and power consumption and reliability of sensors and systems.
The vehicle will fly by using a lifting gas, hydrogen or helium. This method of flight was chosen because it does not use energy to create lift, and so flight time is theoretically indefinite. This vehicle is designed to use global wind currents to provide useful flight paths, and so its energy usage for movement in 3D space will be limited to controlling altitude. Some calculations involved include buoyancy forces, how volume and lift change with altitude and temperature, expansion and contraction cycles and balloon life expectancy, and gas diffusion of the lifting gas through the balloon material.
The physical prototype we are designing will achieve 4 functions. It will aim the solar device, collect solar energy, float with helium, and control its altitude.